Group 14 elements mainly have carbon, silicon, germanium, tin, and lead, while first two are
Mm-hmm.
metals, non-metals. The third one is metalloid, and the last two are metals.
Right.
Size is uniformly increasing, but as it comes to tin and lead, the size is almost the same. Although lead has slightly higher, but the change in the difference in the size is very, very less. And
Right.
we counted on the basis of lanthanoid contraction.
Yes.
Now, when it comes to ionization, as you go from carbon towards lead, it is supposed to decrease, which is how naturally we expect as the size increases. But when it comes to tin and lead, slightly lead will have edge over the tin here. Okay. And
Okay.
electron gain enthalpy decreases in a regular order. Electronegativity is very interesting. Carbon has 2.5, while silicon, germanium, tin has 1.8, and lead has 1.9.
Nice.
This is slightly higher compared to that of these three. Okay.
Right.
Density wise, also down the group, it increases, right? Only
Mm-hmm.
difference here is if you are comparing carbon with the graphite solid compared to that of diamond solid. In the case diamond, then it will overpower the silicon form. Otherwise, silicon has more than that of graphite. Okay. Next, melting point. If you go down the group, tin would have relatively more melting point. Melting point has to do more with the metallic bonding. So the metallic character of tin would be more because the participation of electrons is more easier in tin as compared to that of lead.
Right.
And boiling point has to do more with the molar mass. Molar mass wise, if you notice, lead will have more molar mass, and that will account for better boiling point here. Okay,
समझ गया.
so this is the part that explains boiling point. Then next,
Right.
right? If you notice the oxidation states, carbon showcases anything from -4 to +4. Same goes with silicon. While germanium, tin, and lead does not show anything in negative, it only shows from 0 to 4.
Right.
Germanium and tin, they can show +2 and +4. In both of them, +4 is more stable than +2. While lead, which
Right.
shows +2 and +4, +2 is more stable than +4.
In
And this
not pair.
accounts for inert pair effect. Inert pair effect is the ability for s orbitals not to participate in bonding. And why that happens?
Right.
Because of lanthanoid contraction, 4f electrons are strongly 4f electrons will
Poor
give a poor
shading effect.
staining, so because of which 4s are strongly attracted.
Yes, sir.
That's why SnCl2 is regarded as a very good reducing agent because it can convert into Sn+4 more easily. So may it
Right.
be iron Fe+3, copper 2 plus, Hg2 plus, gold 3 plus, MnO4 minus or Cr2O72 minus. These are all oxidizing agents in front of SnCl4. They all will get reduced.
Right.
Okay.
Okay.
Next. Typically, when you compare the nature of bonding, 2p and 2p pi bond will always be greater than 2p 3d, 3p 3d, and 3p 3p. Correct? This is something which we
2P,
know.
2P, 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 3D, 3P. Yeah.
Now, when it comes to carbon, it can make a double bond and triple bond because it is about 2p 2p overlapping.
You're right.
While silicon, if it has to make it as a double bond with another silicon, it has to overlap between 3p and 3p. And you could notice
Okay.
3p 3p overlapping is very poor. That's why you will hardly notice anything where silicon has a double bond.
Right.
Got it. On
Yes,
the other
sir.
hand, silicon, instead of making a double bond, it will start making a structure like network like structure, which is like what happens in diamond. So it starts involving
Right.
with all single bonds like this. So this will form a
Okay.
three-dimensional tetrahedral unit very similar to diamond.
Right.
Next, carbon dioxide gas exists unlike SiO2, which exists as a solid polymer. Again, because of the
Okay.
bond strength. C double bond of bond strength is high. Si double bond O can exist, but it does not create that level of bond strength as much as the sigma bond what it can create. So instead
Okay.
of involving into one sigma, one pi, it will involve into all sigma bonds. and that
समझ गया.
helps it gain into a giant molecule structure. Okay,
Okay.
this is how the silica exists. Next, you notice nitrogen with silyl group SiH3. This is planar as compared to that of N-methyl group. Okay, tertiary methyl amine. This is because in methyl you do not have any empty orbital on carbon to accept lone pair on nitrogen. While
Right.
when it comes to silyl group here, nitrogen's lone pair can easily be accepted by silicon's empty d orbital, thus making the nitrogen into sp2 hybridization and planar structure.
Right.
Okay, so this will give us 2p3d pi overlapping. Got it?
Right.
Next. Now this is something which we need to know about silicon and carbon. What are the typical reactions of group 14? You see, with water, it will involve carbon, silicon, germanium. They do not react with water, but tin and lead reacts with hot water or steam. Okay.
Okay.
In fact, tin, when you react with H2O, it will become SNO2 and releases H2 gas. Lead on heating will become PbO and H2 gas. While
Okay.
PbO problem here is PbO can become a passive layer on the surface of the lead. Therefore, the reaction stops after a while.
ठीक है.
These does not involve into acids. Okay, so carbon, silicon, germanium, they are unreactive in acids, while lead and tin get dissolved in dilute acids and convert them into higher oxidation states with H2 gas released.
Okay.
Now, graphite, when you react with concentrated HNO3 in a hot condition, then the graphite structure might convert into this kind of acid. It is known as mellitic acid, where COH is present on all the positions of benzene ring. Okay.
Okay.
On the other hand, silicon can give simply SiO2, and SiO2 when you react with HF. This is the most important reaction in this topic. How silica, when you react with HF, first convert into SiF4, which is a soluble form, and that
हाँ.
SiO4 in water will, with further HF, will convert into hexafluorosilicic acid. It will convert into
Hexafluorosilicic
hexafluorosilicic
acid.
acid.
Okay.
Okay, clear. Next, if you notice reaction with bases, carbon does not make any reaction while silicon get dissolved. Silicon, when you react with NaOH, will convert into Na2SiO3, which is a water glass. Okay, and alongside it will release
Okay.
H2 gas as well. Now,
Water
germanium,
glass.
tin, and lead. Water glass, as in the main component of the glass, beta, in liquid form.
Oh. Okay.
Tin, lead, and uh, germanium, when they react with NaOH cold or hot, they will also get converted into this uh, glassy form, that means an oxide form, salt oxide form, and releases H2 gas.
Right.
While carbon does not react with fluorine directly, but graphite, when you react with a high temperature, can form into a non-stoichiometric form of fluoride. Okay. While
Right.
silicon germanium reacts with all the halogens, convert into SiX4. Okay. And same
Hmm.
is the case with germanium also. Lead can react with fluorine in cold conditions to become PbF3, and Cl2 in hot condition to become PbCl2. Okay. With
Right.
Fe2, F2 can become SnF4, and with others it can become SnX2. All right.
Hmm.
These are reactions with halogens, how they happen with various cases. Now,
Okay.
carbon, when it is existing as CF4, CCl4, CBr4, and CI4, this
Right.
is gas, this is liquid, and the other two are solids.
Solid. Yeah.
Stability wise, down the group, the stability decreases, because
Right.
carbon fluorine bond is very strong as relative to carbon iodide.
Right.
Now, this is very interesting. When it comes to CF4, if you add it to water, it will remain inert. That means it is acting like a non-polar liquid in front of H2O.
H2O. Yeah.
Okay, clear? Why? Reason
Yes,
being,
sir.
carbon does not hold any empty d orbital to accommodate. At the same time, fluorine is not a good leaving group, so that the simultaneous
Right.
attack on removal can favor. Hmm?
Right.
But when it comes to chlorine, when it comes to CCl4 here, now chlorine is a good leaving group. So when water attacks, automatically chlorine will leave. So after two chlorines leaving, you will get a
Hmm.
gaseous form known as the phosgene gas. So it will not go
Okay.
for further reaction, but it will keep on happening, and it keeps going towards phosgene gas. But if you compress that gas and react with H2O further, I mean, add it in moisture, that is, eventually it will convert into carbon dioxide. So it will react the other chlorides also and convert into carbon dioxide.
Which gas if you compress and react with water?
Phosgene gas.
Phosgene.
Okay. Phosgene is a very harmful gas. Okay. And now, see, due to steric factors in SN2 is not possible. Hence, SN1 is mostly adapted in these conditions, which means first Cl minus will leave like this. This is the rate determining step. And after Cl is gone, water will attack on it. Afterwards, chlorine will be removed. That's how phosgene gas has been observed. Clear?
Right.
Rate of hydrolysis, better leaving group, better is the rate here. So that's why iodine will be more than bromine, chlorine, and fluorine.
Iodine, bromine, chlorine, fluorine. Okay. Hmm.
Right. Rate of hydrolysis for carbon halide will be iodine, bromine, chlorine, and fluorine. This is the order in which it will go. And now notice
Right.
silicon halides readily hydrolyze. Okay. This is
Hmm.
due to availability of empty d orbitals and due to large
Right.
size of silicon, steric hindrance is less to attack. Correct.
Got it.
So now water will directly attack on silicon first. It can accommodate because of its empty d orbital. Later on,
Right.
chlorine can leave. Okay, and this Cl minus can take H plus away, convert it to HCl. So you will get this form. And imagine doing it for 4 times. So you will get SiOH4.
एक एक करके Cr
SiOH4 is
replace
what
होता
we call,
जाएगा.
hmm?
Hmm.
And that is what we call it as silicic acid. Okay.
Okay.
Just like how we have boric acid as BOH thrice, silicon is SiOH 4 times, that is silicic acid.
Got it. Hmm.
Now, in this case, the rate of hydrolysis will be different. Have you noticed? For carbon, it is different. For silicon, it is different. For carbon, we learned that this is how it will be. Okay, CBr4, CI4. Why? Because the first
ठीक
step is the
उल्टा था.
RDS here, correct?
Yeah.
But here, the first step is not the first step is the RDS, but that is not the removing of group. First, it is about addition on silicon. And silicon, if it has more delta positive, easy addition can take place. That's why
Right.
fluorine is a better withdrawing group. So that's why it can make a better hydrolysis for here. Okay.
Right.
That's why you see SiF4 when you react with water molecules, it will become SiOH4 plus HF. Okay. Now, once the silicic acid is forming here, have you noticed that if I take whatever the HF which is forming, the same HF can further react with SiF4, convert into H2SiF6. So if I add all of them, you can see 3 moles of SiF4 with 4 moles of water is converting into 1 mole of silicic acid and 2 moles of hydrofluoric acid. Clear? This is a partial hydrolysis that you need to remember. For fluorides only, the partial hydrolysis will take place.
Okay.
In the case of chlorine, bromine, iodine, complete hydrolysis will take place. That means it will convert into silicic acid and HCl or HBr or HI.
ठीक है.
Rate of hydrolysis, if you compare, SiX4 is greater than XCF4, SnX4, and PbX4. Okay. Because silicon and then germanium, tin, lead, as you go down, the metallic character increases. So ability to accept a nucleophile decreases. Got it? And H2SiF6 can be formed, but this cannot be formed because sterically 6 chlorides on an octahedral structure is not possible with silicon.
Right.
Next, let us compare what about oxides. There are two types of oxides that can be formed here, element O and element O2. Like carbon can form carbon monoxide and carbon dioxide, silicon monoxide and silicon dioxide, and so on. Silicon carbon monoxide is neutral in gas, neutral in nature, while SiO2 and CO2 are acidic in nature. GeO is basic in nature. SiO is hardly observed, so that's why I haven't specified it. GeO2 is amphoteric in nature with slightly more acidic character. But this is most important. All the oxides of tin and lead, they would remain
Hmm.
amphoteric.
Okay.
Correct? Individually, if you notice the compounds, first carbon monoxide, formic
Right.
acid, if you try to dehydrate it, so water can be removed out, remaining part is carbon monoxide.
Right.
Oxalic acid, when you react with concentrated H plus, remove water, you will get carbon monoxide, carbon dioxide, and water.
Hmm.
Next, coke, when you react with O2 in a limited amount, it will become carbon monoxide.
Right.
Okay. Next, carbon, coal with water in the presence of nickel and heat, this will convert into carbon monoxide and H2 gas. This is called coal gasification. This is how you make the carbon monoxide in general. Mhm. In case if nickel is being used, you can control the oxidation and convert that into carbon monoxide. This is coal gasification. Clear?
Okay.
Next, carbon monoxide burns with a blue flame. You know, whenever you bring it to the Bunsen burner, it will give a blue flame to it. Carbon monoxide is toxic form. Carbon forms a carboxyhemoglobin and makes it stable. Then oxyhemoglobin. See, in
Hmm.
hemoglobin, iron would be surrounded with this nitrogen as a complex, and one position it will carry out by oxygen. But if carbon monoxide is been added, this oxygen is relatively, weakly bonded with iron, but carbon
Right.
monoxide will become very strongly bonded. Therefore,
Hmm.
instead of oxygen carrying, it will carry carbon monoxide. Okay,
Right.
so it is almost 300 times more stable than oxygen carrying group.
Okay.
Next, carbon monoxide, when it is passed through aqueous palladium chloride, it gives palladium as reduced metal. Okay, so you can see PdCl2 plus carbon monoxide. It is giving carbon dioxide. Pd will get reduced and HCl will be forming. And next, Fe2O3 plus carbon monoxide. This is metallurgical reaction. We have learned this. CO is used for reducing iron oxides into iron. Okay.
Hmm.
Now here is interesting, reaction. Very interesting reaction. That is, if you take potassium ferrocyanide and react with concentrated H2SO4. Okay.
Mm-hmm.
In that case, the complex nature is lost, and you will get K2SO4. This will become Fe2SO4, and the nitrogen will take away hydrogens from concentrated H plus, converts into ammonium sulfate.
Okay.
Important part is oxidation state of none of them has been changed. Only
Mm-hmm.
their uh, components nature has been changed, but oxidation state has not changed. Same way, if you relate that with dilute H2SO4, this cyanide Cn minus will only take H plus, convert into HCN, K2SO4 and FeSO4. So remember, if you want carbon monoxide, then you have to use concentrated H2SO4. Otherwise, it will become HCl.
Hmm.
Make sense?
Yeah.
Carbon monoxide, if you directly react with chlorine, it will become a phosgene gas. If you react with NaOH, it will, in a fused form, it will convert into sodium formate. Okay. If you react with sulfur, it will become thiocarbonyl group. Okay. So these are few
Right.
important reactions of carbon monoxide. See, carbon monoxide is also used in metallurgy in Mond's process, if you recall. Suppose if at all I had an impure nickel and I added with carbon monoxide around 330 kelvins. First, you will get volatile vapors of nickel carbonyl group, and that when you further heat it, it will convert into nickel as well as carbon monoxide. So,
Wait.
and this nickel,
Nickel,
which is
carbon
coming out to be,
monoxide.
is a much more stable form. I mean, much more purer form that can be collected close to 99% pure. This is Mond's process.
How?
Hmm?
You gave impure nickel, added carbon dioxide and
See,
carbon
what happens
monoxide,
is in
and
the
suddenly you
impure
get
nickel, you
pure
will have
nickel.
certain solids which will be left over. Okay. This impure form, when you react with carbon monoxide, most of the nickel will combine with it and convert it into vapors. And rest of the part which is remaining, those are all impurities. Okay. But I need to break this one also to separate nickel and carbon monoxide, isn't it?
Oh, volatile. अच्छा, that I
Hmm.
didn't see. ठीक है.
Hmm. Next, notice carbon dioxide. Carbon plus O2 will give you carbon dioxide. Any oxidation reactions will give carbon dioxide. Calcium carbonate on heating will give carbon dioxide. Sodium bicarbonate will give you Na2CO3, H2O, and CO2, carbon dioxide on heating. See, carbonic acid, you know, one second, one second. Right, see, the H2CO3, the pK1 value is 5.8 and second one
Right.
is 11.5. In fact, that shows that carboxylic acid are more acidic than H2CO3, phenol, and HCO3 minus. This
Right.
order is useful specifically while you are dealing in GOC, correct? If you recall, this is all something which we have done, which will give positive bicarbonate test. Hmm.
Hmm.
What are the reactions of carbon dioxide? See, with KOH, acid-base reaction will take place. KO2, superoxide also acid-base reaction. Peroxide also acid-base reactions. Okay. Calcium
Right.
hydroxide also acid-base reactions. Only with water in the presence of chlorophyll, it will convert into glucose, photosynthesis.
Right.
And only with oxide also it will become acid-base reaction and convert into carbonate. The most stable form of carbon dioxide is carbonate only. So that's why it would try to make an acid-base reaction convert into carbonate form. Okay.
Right.
Next. Second, notice what is silica. Okay. What is the reaction? What are the reactions of silica? Silica is mainly found
Mm-hmm.
in quartz and sand. It is a covalent polymer solid, like it will have a link like this. Okay. So where
Right.
it is connected with all four directions with oxygens.
Right.
There are three common type of silicas. One is quartz, one is called tridymite, the other one is crystallobelite.
Cristobalite.
Okay.
Right.
Within the quartz, I have two kinds, alpha and beta quartz. Same with tridymite and same with crystallobelite.
Right.
And usually beta forms are thermodynamically more stable, and stability keeps increasing towards crystallobelite. These are types of sands you can understand. Okay. So sands are also multiple kinds of sands. Some sands will break down very easily, some are extremely hard. The ones which are very hard, those are crystallobelite. Okay.
Hmm.
They sustain very high temperature. Now out of this entire thing, what is one thing you should know is that almost around at 1700 degrees Celsius, everything will convert into liquid silica. Adi clear beta?
So, what is the structure of alpha versus beta?
Alpha and beta quads would have structural differences in solid state only. Okay, which means
Okay.
if one is adapted as ABC kind of arrangement, okay, the other one will be AB kind of arrangement. Okay, so typically they would start changing from FCC to HCP kind. Okay,
And I have no idea what those mean, but okay.
yeah, we'll discuss it as we go. Okay. Mm. Now, SiO2 does not react with any acid except for HF and silica. This is one important area that when you react with HF, it will become SiF4 and water. But you can see this is the third time we are writing the same equation. So SiF4,
Hmm.
when you react with HF excess, will convert into soluble acid, which we call it as hydrogen hexafluorosilicic acid. Okay,
Yeah.
H2SiF6. See, SiO2 being an acid reacts with NaOH, converts into Na2SiO3 and water. And if you treat with
Mm-hmm.
F2 also, it will convert into SiF4 and O2. And the same
Right.
treatment is not observed with chlorines.
Right.
See, next, hydrates. See, this is an important area again. Hydrates, carbon can form so many different hydrates, correct? It can form alkane,
Right.
alkene, and alkyne. Hmm? While
Yeah.
silicon can form alkane type, which we call it as silane. Just like we call it as alkane, here we call it as silane. Hmm?
Okay.
And these silanes does not go beyond 8 carbons, 8 silicons. Okay.
Okay.
So maximum they can have is SiH4, Si2H6, Si3H8 like this. Okay. More like alkane, alkene, and alkynes.
Yeah,
Correct.
okay.
While germanium can form a similar type of compound known as germane, but those germanes will also be stable only up to 5 carbon, 5 germaniums.
Five Germany.
In the case of tin, you will have SnH4 and SN2H6, and lead will have only one form, PbH4.
Yes.
So these are the only hydrates we can think of. Okay. See,
Yes.
properties wise, if you notice, all of them are sp3 hybridized, and
Right.
obviously down the group, the bond dissociation decreases because lead
Uh-huh.
being larger in size, it is easier to break. Thermal
Right.
stability will also be stronger and it decreases down the group. Reducing
Right.
nature increases down the group because lead bond itself is weaker, so that means it can provide hydrates more easily.
Right.
And since they are all non-polar, boiling point mainly depends on molar mass. Higher molar mass, higher is the boiling point. That's why PbH4 will have high boiling point. Okay.
Right.
All of them have equal bond angle. Remember that 109 degrees 28 minutes. Equal bond angle. Next. Next is, see, carbon hydrides are less reactive, but other hydrides are readily reactive. Okay, readily reactive with nucleophile because its hydrides of carbon bear delta negative charge, but others possess delta positive charge. Okay,
Right.
because you can see the electronegativity of all of them. Only when it is combining with carbon, hydrogen gets hydrogen as delta positive. But with all others, it will have delta negative. You can see with silicon, with tin, it will usually have delta negative sign on it. Okay,
Right.
next. Again, methane does not have an empty orbital, so it does not react with water. But silicon, germanium, tin, they all have empty orbitals, so water can attack them. And on from the other side, H minus can take this H plus, convert into H2. Got
Right.
it? And CH4 can give a complete combustion. SiH4 can give a complete combustion, and combustion in both the cases is negative. That means energy is released overall.
Right.
If binary compounds of carbon with less electronegative are carbides, that means if carbon is connected with some metals, it becomes
Mm-hmm.
carbide. But if it is connected with a more electronegative element, like halogen or oxygen, sulfur, phosphorus, then it is not considered as carbide. I cannot say CO2 is a carbide. I cannot say CS2 is a carbide. But
Okay.
CH4 is a carbide, correct?
Yes,
Understood.
sir.
So we need to have, and metal, any metal with carbon is a carbide. Hmm.
Okay.
See, there are three types of carbides. One is ionic carbide, covalent carbide, okay, and metallic carbide. See, ionic
Okay.
carbide, it possesses ionic bond with carbon, and these ionic carbides are of, you know, three kinds. One is methanides, acetylides, and propanides or allylides.
Right.
Propanides are also called allylides. Now, beryllium and aluminum, which possess a diagonal relationship, they have two carbides existing, Be2C and Al4C3.
Right.
And both, when you react with water, will release methane gas.
Right.
So that's why they are called methanides, because they release methane gas on hydrolysis.
Right.
Second, acetylides. Other acetylides are copper, silver, gold, zinc, cadmium, along with lanthanides, which includes calcium oxide plus carbon, CaC2 plus CO.
Right.
CaC2 on hydrolysis will give you this calcium will convert into hydroxide, and this will convert into acetylene.
Right.
Well, in case if at all I take calcium carbide, react in air which contains nitrogen, you will see a compound calcium, calcium isonitride here. This one, if you react with further carbon and water, it will convert into a urea form. And
Urea.
urea, if you hydrolyze it further, it will convert into ammonia and carbon dioxide water.
Okay.
Okay. Now, this mixture of two compounds, right? This is called nitrolim mixture.
Nitrogen mixture.
This is called nitrolim mixture.
Okay.
Next one is allylides. See, C3 4 minus. If you have and that hydrolyze it, so it will convert into C3H4, which will look like this propine form. So this carbon having 3 minus, this carbon having minus, and on hydrolysis we'll get here as 3 hydrogens, here as 1 hydrogen. So this will become propine.
Right.
And next, if you compare covalent carbides, right? B4C, SiC, these are covalent carbides. Okay.
Hmm.
And even TiC is also covalent carbide. In fact, SiC is having a name carborandum. Okay. And
Carbo
silica,
random.
hmm,
Bro. Okay.
silica, when you react with 3 moles of carbon, so it will convert into SiC and carbon monoxide. You can
Okay.
directly react with excess of carbon also, but excess of carbon will lead to formation of silica completely. Okay,
Hmm.
right. This is the way you can get uh, SiC form. Next, covalent carbides are very hard, chemically inert, and high melting and boiling point because of its giant molecular structure. In fact, SiC structure is very similar to diamond, in which alternative positions of carbon are occupied by silicon. Okay,
Yeah.
clear?
Yeah.
Right. Next, interstitial carbides. The third one is interstitial carbides. See, this is formed by transitional elements and some actinides and lanthanides. Okay, transitional elements, some actinides and lanthanides. Now, these are very hard, infusible, and possess high melting point here. Correct? Now,
Right.
notice metallic properties like electrical conductivity, okay, electrical conductivity, lustrous nature, that means the shiny nature on the surface. These are all retained in the carbide forms. Okay. And
Right.
these forms, when metals and their oxides are heated with carbon around 3000 degrees centigrade, then it will convert into
Hmm.
that form. Okay. And
Right.
most of the time, octahedral voids of metal lattice are occupied by carbon atoms. Okay.
Right.
And if atomic size of the metal is more than 1.35 Armstrong, then the carbon does not distort the crystal lattice. But if the metallic radius or the size is less than 1.35,
Three
then the
five.
lattice of the metal is distorted.
Right.
इसका मतलब क्या है कि if the metal is a much bigger in size, the carbon can fit in the voids very easily without disturbing its geometry. Correct?
Hmm.
But if the size becomes slightly smaller, so it cannot fit in the voids. So now it has to disturb the lattice structure of the metal itself.
The whole interstitial thingy.
Correct. Clear?
Right.
Next. Clear? Hmm.
Yes.
Next, you see the smaller metal like vanadium, chromium, iron, manganese, etc. They form carbides like this V2C, Mn5C2, Fe3C, Cr2C, and so on.
Right.
Alright.
Wait, how does Fe3C make sense?
These are all interstitial forms, na beta. So they do not have any stoichiometry balanced. Okay.
अच्छा, okay, हाँ.
So for a large segment of iron, you will have some small number of carbons present in the voids. Okay.
अच्छा, like for every three carbons, three iron, you have one carbon
Yeah, yeah.
types.
Mm.
Okay.
Next. What about silicones? Okay. The organosilicon polymers contain SiO-Si linkages. These are all called silicones. They have
Okay.
general formula like this. Silicon with R and R above and below, and then there is an oxygen connection to it.
Okay.
And imagine this is stretching as a polymer. Okay.
Right.
Usually, silicones are prepared by alkyl chlorosilane, that is RX SiCl.
Okay.
And X plus Y should be always equal to 4.
Right.
Right. See, organohalides can be prepared by treating SiCl4 with RMGX or RLI. You can see
Right.
2 moles of RMGX when you react with SiCl4, you will get this as R2SiCl4 and 2 moles of MgXCl. Okay.
Right.
And now you got this as R2CI SiCl4, correct? How would I get this? See, check this an example. Methyl in case if you have. You will get dimethyl silicon dichloride.
Right.
Correct. So this is how it
Yes,
will
sir.
form. But if you take excess amount of Grignard's reagent, it can
Mm-hmm.
remove, you know, uh, only one chloride here, and you will get SiCl3. Or you can remove two
Right.
chlorides, you can remove three chlorides, or you can remove all four chlorides.
All four
And
chlorides. Yeah.
because you are using this as excess, all four chlorides coming as major product. Hmm.
समझ गया. और wait, और अच्छा हाँ, okay, sorry. Okay.
Another way of preparing this is you heat methyl chloride with silicon powder at around high temperature with in the presence of copper. In that case, 70% will be this one, rest will be around 30%.
Okay.
Industrially, this is more used to prepare dialkyl silicon chloride.
Hmm.
Now notice, alkyl fluorosilicates on hydrolysis undergoes polymerization by condensation.
ठीक है.
Okay? But similar derivatives of carbon produces ketones. That is, if you have two chlorides here, you remove these two chlorides with two OH groups, and these two OH groups will convert into a double bond, which is a keto
Right.
form. Okay. And here same way, two silicons, if two chlorides, if I replace that with OH group here, you are expecting this to form similarly as a keto form, but double bond silicon is not very stable as much as double bond oxygen, so it would
Hmm.
relieve to be existing more in the single bond form.
Okay.
Now as you heat it down, what happens in basic medium, because you're still taking it a basic medium, so OH minus will take H plus from here, and this O minus will again back attack on silicon to remove this OH minus. That leads to
Oh,
formation of
I
the that leads to formation of that polymeric form. Okay, and that's how you can see
yes, sir.
silicon, oxygen, silicon. This kind of linkage has been established here. Are you clear with that?
Yes, sir.
Okay. Now, one thing we learned that this is a linear silicon. Linear silicon means ये extend हो रहा है self linearly. Okay.
ठीक है.
Now, if I take trialkyl chlorosilicane, right? That means if you have
Right.
three alkyl groups and only one chlorine, so you'll get one OH group here. And in the
Right.
presence of OH minus, you see this water will go, and what do we get
समझ
here?
गया.
You'll get only one product, right? So basically a dimer type
Yes,
of
sir.
product is established. Okay.
Got it. Hmm.
So R3SiCl is used as a chain terminating group. So imagine यहाँ पर ये बढ़ते जा रहा है chain. So at the
Hmm.
end, I need to terminate on this side and this side. So what is the best thing what we can do is add 2 moles of R2SiCl, R3SiCl. Okay.
I see.
So at the ends, it will stop the reaction
Terminate.
from extending. Okay.
खत्म. ठीक है. Hmm.
This is trialkyl fluoro. Next,
Right.
type of silicones. Okay. What are the types of silicon? See, if I take R2SiCl4 and you extend polymerically, it will form linear silicons. That's what I told you, right?
Yeah.
At the same time, if you use the limited amount of water, that means controlled hydrolysis is being done with a high pressure, then water molecules can relieve within the molecules like this and convert into a cyclic structure. So this is three
Okay.
cyclic silicones. Okay.
Okay. Yes, sir.
You will get a cyclic structure here, and cyclic structure can be 3, 4, 5, 6. That means 3 silicons forming a cycle, 4
Four
silicons forming a cycle, or
silicons.
5, 6 silicons. Okay.
Okay. Hmm.
Next is cross-linked silicones. Cross-linked silicones as in RSiCl3, when you react with water, all the chlorines will go away, OH will come here. So if you have only single alkyl group, then
Right.
they can start extending on 3 directions here, like this. Got it?
Got it.
So this is called cross-linked silicone. Next, generally silicones are resistant to heat. They are electrically insulators. Okay.
Okay.
And in fact, they are chemically inert due to its strong silicon oxygen bond and silicon carbon bonds.
Carbon bonds.
So they
Hmm.
are water repellent because of the hydrophobic nature. Okay. As they have an alkyl group on the surface always, it is hydrophobic. Okay.
Right.
That's why wherever we see silicon made goods, they do not uh, absorb water at all. Okay. They'll be
Yeah.
strongly repellent. This is about silicones. Now let us say silicates. Silicates are the
Mm-hmm.
salts of silicic acid. Okay, so that means if you
Okay.
take silicic acid is SiOH 4 times, and that when you react with NaOH, it will become SiO4 4 minus. Now
Right.
this silicates SiO4 4 minus, that becomes the basic unit, and this basic unit can keep connecting with each other. That is, when we treat that in the presence of acidic medium, first let us say O minus will take one H plus, and another molecule also, another position will take one OH. So you can remove the water from here and make the connection. So silicon O and silicon, this is the connection we get.
Right.
Okay, so what do we have here is Si2O7 6 minus. Okay, so these are the silicates which you have.
Okay.
Remember the formula, Si2O7 6 minus. Okay. Hmm.
Si2O76 minus. Okay.
Usually, there are so many several types of silicates. To represent their structure properly, we have adapted a structural representation. Now, because this is tetrahedral in nature, correct? So, tetrahedral in
Hmm.
nature means it would appear like this, isn't it? If you notice, this is how it will appear, correct? Like a
Yeah.
tetrahedral.
Yeah. Hmm.
In a tetrahedral, what you do, if you view it from the top view like this, okay, when you make it a top view, you can notice that this O minus will, just be on the top of the silicon,
Yeah.
and these three will form a triangle, equilateral
Yeah.
triangle around it. So this is a top
Correct.
view which we need to adapt. Okay.
Okay.
Now this line does not have a bond. This is just to represent how the structure looks like. Okay. This is clear. These three are not the bonds. Actually, this dotted line is what is the bond. Okay.
Right.
So now notice from here, this is the silicon. The dot here represents silicon. Okay. So there is a dot on top of that. On the top view, there is an oxygen which is connected. And
Hmm.
now on the sideways, you have two oxygens. Here two oxygens, and central oxygen is shared. Clear?
I mean, but how is that central oxygen shared?
Hmm?
How is that central oxygen shared?
We just got this here, no? But this
How
one,
does it have six bonds?
central oxygen is no six bond. That's why I told you these are not bonds. This is just a
अच्छा
structural
sorry they're just
representation.
the structure ठीक है
Uh,
मैं इसमें से
this is just to
confused हूँ
represent the structure. That's why I told you the first thing. Don't think
हाँ
that as a
ठीक
bond. Bonds are these
हाँ
three.
ठीक है
Okay, take, I'll change the color also. These are the bonds. Okay.
yes sir.
Now they are classified into different types, starting with orthosilicates. Orthosilicates means there is no oxygen which is shared. Okay.
Okay.
So simply we have SiO4 4 minus. And now
Okay.
that 4 minus can be connected with something like zirconium, which can exist as Zr4 plus, or 2 moles of
Right.
zinc, which will be 2 moles of Zn2 plus, 2 moles of beryllium, 2 moles of magnesium. With zircon, we call it as zircon. That is the name of it. With
Okay.
zinc, it is called willemite.
Willemite.
Beryllium, it is called phenacite. And with magnesium silicate which is formed, that is olivine or forestite.
Okay.
Next, second one being pyro or disilicates, which we just learned. Two silicates if they
Hmm.
connected with a shared oxygen. So we learned that
Right.
Si2O7 6 minus. This is called pyrosilicates or disilicates. Okay.
Hmm.
So you can see 6 minus it need to be balanced by the metal charge. So 3 moles of zinc will balance it, or 3 moles of scandium can balance it. Sorry, 2 moles of scandium can balance it. Okay. So this is hemimorphite. The name of that silicate is hemimorphite. Cyclic silicate. See, if two oxygens per unit of silicate are shared, then you will get this formula. Notice, see, this
Right.
is how the structures has been, okay, like this.
Hmm.
So if you notice any one of the silicon here, let's say this is the silicon, it is connected through four oxygens, one on the top and three on the sides, correct?
Right.
And now the top oxygen, if you notice, correct, is
Mm-hmm.
open. This is open, this is open. While this is open, and this is open. So that's how you got,
Bruh.
right? So you can get this as Si 3O9 and 6 minus. Okay.
Okay.
If I take the commonality here, so 3 can come common. So you can get it as SiO3 thrice N 2N minus. Okay.
Oh.
So if you see this one, right, you should know that we are talking about cyclic silicates.
SiO3 N times SiO3 N times. Yeah, I mean three
Done?
O3 O3. Yeah, makes sense. Hmm.
Next. Next one is beryl. Okay. Now,
Hmm.
what is the structure of beryl? You see, Si6O18 12 minus. Clear?
Okay.
That is beryl. Now, first what you do, make six silicons. One, two, three, four, five, six, just like benzene. Okay?
Right.
And between those bonds, keep one oxygen. Done. Insert one
Hmm.
oxygen. ये भी हो गया. And thereafter, now you start sharing the ends. One, two, three, four, five, six. And thereafter, you
Okay.
can share one on the, I mean, you can put one oxygen on the top. Done. That's how you make up the structure.
Bro. Okay.
Now, in this case, how many open oxygens are there, beta? See, these are all open. One, two, three, four, five, six. Correct. The top one is also
Yeah.
open, no?
Yeah.
So total how many? 12 are open. So open means
12.
that will have open valency, which is 12 minus.
Hmm.
और 12 माइनस को मुझे बैलेंस आउट करना है. दैट्स व्हाई आई कैन टेक 2 aluminiums and 3 berylliums.
6 6. Yeah. Okay. Hmm.
Clear?
Makes sense.
Right. So this is beryl, and most used one is beryl only. The other forms which are of a similar kind is benotinite and vonastonite. But like these are not the names which you are supposed to worry about. Okay, only beryl is very important. So learn how the beryl looks like,
What
correct,
is the structure
structurally.
of these two? I don't need to know now.
No, they will be similar kind. Only the metals will change, na beta. Hmm? Because
हाँ
formula
मतलब
is the
which
same.
metals are there that I don't need to know
That
now.
you don't have to worry. Hmm.
ठीक है. Okay.
Next, chain silicates, also known as pyroxenes. So here in chain silicates, two oxygens of SiO4 are shared linearly,
Hmm.
like this. Here, from here to here, first, basically this is like a pyrosilicate extended version. That's it. Okay.
Hmm. Repeating pyrosilicate. Hmm.
Yeah. So here, so that means per silicate there are two oxygens which are shared.
Right.
So if I take any one silicon as a reference, out
Hmm.
of four, two are unshared. So it will have SiO2 with 2 minus, which is unshared, plus O3, which is oxygen, with right. So this is the one which you have. Okay. So
Right.
SiO3 2 minus is what you will get. Okay. Hmm.
Yes, sir.
Spodumene is with zinc. Okay. Astatine,
Sport.
diaspide. These are all the forms of chain silicates. Spodumene
Right.
can be asked, which is with zinc. Okay. Hmm.
Yes, sir.
Next, double chain silicates, also known as amphiboles. Double chain silicates are called as amphiboles. Now, in these
Amphiboles, okay.
silicates, some silicates are sharing two oxygens and some are sharing one oxygen.
Someone sharing two oxygen. Yeah, okay.
Now, how does that work? Check it out. This is the general formula you will get. SiO2O5N2 minus or Si4O11N6N minus. Okay. Now, this one is a much easier way to prove. Check it out. First, check out this silicate versus this silicate here. Okay. Now, in this silicate, have you noticed there are two open-ended? This one and this one are open-ended. These two are shared.
Correct.
Correct.
Yeah.
So, which means silicon will have SiO3 2 minus because
Yeah.
this is half and half because both
Correct.
of them are
Correct.
shared. This is complete one and this is complete one. So, that makes it three
Correct.
oxygens total.
Yeah.
And overall charges, because these two are open valencies, it will have 2 minus.
2 minus, yeah.
Now come to this silicate now. In this silicate, this silicon is shared with one here, and one here. So which means half, half and
Half,
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 correct?
half, and then one beach mein.
One beach mein, upar. So that is not shared. So which is 5 by 2. Overall
2.5, yeah.
oxygens are 5 by 2. Hmm?
Hmm.
And open valence is
Charge
only
is
minus 1.
zero. Acha,
Upar.
minus
So
one,
minus
sorry.
1.
Beach wala hai.
ठीक है ऊपर वाला open है.
Yeah.
Now this is the structure what you'll have. Correct?
Yeah.
To make it more uniform, multiply everything with 2. So what do I get? This will be Si2O6 4 minus and this will be Si2O5 2 minus.
Acha, and then you get
Add all
Si4O11
of them.
6
So what do we
minus.
get? Si4O11 6 minus.
समझ
Done.
Makes sense. Makes sense. Yes, sir.
Right. Now in JEE questions, the structure would be given to you and you are expected to predict the structure like this. Okay. So I think now you can do it, right? So you
Yeah.
just have to take the commonalities and see which one is the least possible formula you can get. Hmm?
Hmm.
The usual asbestos which you notice, right? Okay.
Hmm.
Those are all made up of double chain silicates. So corcidolite, which is blue asbestos, brown asbestos, amosite, these are all made up of double chain
Asbestos
silicates.
is that thing which, if you inhale, it causes problems.
Yes, yes.
Ah.
Next, sheet silicates. Three oxygens are shared, except one oxygen, the open one, the top view one oxygen which is left. Except that all three are shared. Okay. So if three are shared, you can say that SiO, this O is unshared, and this O with 3 by 2, O raised to minus 1.
Hmm.
This will be the form. Next, if you make it into normal or common form here, so I can get it as SiO5 2 minus. Finished? See, talc, pyrophyte, okay, crystotite, which is white asbestos, muscovite, which is mica, okay.
Hmm.
So these are all the forms which are sheet silicates. Got it?
पर इसमें भी बीच में ऑक्सीजन है ना?
है ना? Right?
हाँ.
They are all connected here. Correct. On three sides. Next.
हाँ नहीं नहीं, और सेम बीच में ऑक्सीजन है ना, वो ऐसा है के ऊपर.
हाँ ऊपर है. One
ठीक
oxygen
है.
here. Okay.
ठीक.
Next, you see 3D silicates. All four oxygens, if they are shared, then that will become 3D silicate.
Quartz,
That's it. This is
crystallite,
what we learned.
tridymite.
Quartz, crystallobelite, and tridymite. These are all what? 3D
3D
silicates.
silicates,
Okay.
silica.
Clear. So 3D silicates with all silicons atoms shared, they do not have any charge on it. But in most of
Okay.
the minerals, either one fourth or half of the silicon atoms are replaced by aluminum. Okay.
Right.
Naturally occurring silicates, they usually have some replacement of, metals here. Got it?
Hmm.
So you see, the negative charge produced by the neutralized by larger cations like sodium, potassium, magnesium, aluminum, and so on. Okay.
Right.
For example, here in this case, you will notice that
Right.
instead of this Si4O8, imagine one of them is aluminum occupied, and then silicon, which is left here. Total, we have four of them, correct? Out of which
Yeah.
one of the silicon is been replaced.
Hmm.
So this is the form what you will get. And because aluminum has +3 charge, so 1 minus 1 open valency will be still left. And that is being neutralized by sodium, potassium, and rubidium, and so on. Okay.
Right.
And this is one fourth of the silicon replaced. Sometimes two silicons can be replaced. If two silicons are replaced, I'll get this as Al2, SiO2, and O8 2 minus.
Basically, you can replace some amount.
Yeah.
ठीक.
After the replaced form, you will get these like stones beta. Okay. And these are called
Stone.
zeolites.
Okay.
In the coral reefs, you see, right? Okay. In the
सर ऑस्ट्रेलिया
reefs.
में तो आप बैठे हो ग्रेट बैरियर रीफ के पास. हमारे पास तो कोई है नहीं सर.
Right. So I'm saying generally you may have heard, you might have seen the stones, correct?
ओके.
So chalk piece जैसा दिखता है वो, right? Stones, but they will all made up of what do you say? They'll have some perforations in between. Hmm?
अच्छा आई डोंट नो. ठीक है.
So those are all zeolite forms. Now,
ठीक है.
see, feldspars are the same ones, correct? These are
हम्म.
all the feldspars also. इनको भी feldspars कह सकते हो. Zeolite और feldspar में usually different water content का difference होता है. Okay.
ठीक है.
So orthodox, Clasian, these are all different names of the feldspars. Okay.
ओके.
Now see, zeolites can absorb water, alcohol, ammonia. That's why they are particularly
वाटर
used in purification of water.
अल्कोहल.
That
ठीक है.
water filter candles, if you may have heard of all, correct?
यस सर.
They're all zeolites only. Okay.
अच्छा ओके.
Next, you have ultramarines also, which we see it in coral reef. Okay. So where the stones are very
कोरल
much
रीफ.
colored. Okay. They are all
ठीक है.
extremely colored structures दिखते हैं. That is because
ओके.
of sulfur-sulfur linkage between the feldspars, or sorry, zeolites. If you
या.
have sulfur-sulfur linkages, that polysulfide linkages will give are responsible for showing that color. Okay.
ओके.
And we call them
या.
as ultramarines.
हम्म.
Done? Now, what are the allotropes of carbon beta? Carbon has mainly three allotropes, okay, which we need to learn. One is diamond, graphite, and Buckminster fullerenes. Okay.
राइट.
See, diamond is sp3 hybridized. It has FCC type of structure. If you don't know that, don't worry about it. We'll be learning that soon. So it has an FCC
सुपर बाय.
structure form. Next, it is covalently bonded between all the carbons in a three-dimensional structure. It is extremely hard and have high melting point.
राइट.
Okay. And next, it is diamagnetic and it is a bad conductor of electricity. Its refractive index is high. Okay. It is around 2.6. It is highly
राइट.
thermally conducting, correct? Which is more than graphite. In fact, it is more conducting than graphite. Thermally, it is more conducting. Electrically, it is a bad conducting. Okay.
राइट.
And the bond length between the carbon-carbon is 1.54 Armstrongs. These are the
Right.
basic crux of diamond. Now, coming to the graphite. Graphite will have this sheet-like structures, beta. Okay,
Hmm.
each graphite will have 3 bonds on it. And because there is one extra electron present on carbon, on each carbon, they will internally make a partial pi bond character like this. Okay, so
Right.
it looks more like benzene form only. Understood?
Right.
So now the bond order will be 4 by 3. Okay, because this type of pi bonds, if you notice, they can be made it into uh, you see here, out of 4 bonds here, 3 structures will have similarities like that. Okay,
Hmm.
so just like canonical structures, how we can put it. Clear? Mm. Understood? Right.
Right.
Now bond length will be equal to 1.41 Armstrong. So what is that you notice here? Bond length in diamond is larger than bond length in graphite.
Okay.
Okay. And not just that, when it comes to graphite has a layers, above and below. So if you have one layer
Huh.
here, there is one layer above and one layer below. So there is
Hmm.
a distance between the layers also, and this is called interlayer distance, which is around 0.34 nanometer.
Yeah. Okay.
Okay, or 3.4 Armstrongs. Clear?
3.4 Armstrong.
Of
Yeah.
course, it has
Okay.
to be larger because there is no chemical bond there. It is a van der Waal interaction. Hmm.
Right.
Now, see, overall, graphite is a diamagnetic molecule because those unpaired electrons are not something which are remained unpaired always. They are forming a bond with the adjacent carbons. Okay,
Right.
that's why it is still diamagnetic. Its electrical conductivity is high because these electrons can keep moving from one terminal to the other terminal. It can be used as lubricant because of its planar structure. And
Right.
thermodynamically, it is more stable than diamond. You can see bond energy is higher between carbon and carbon here. That's why
Hmm.
thermodynamically, graphite is given more significance than diamond. And that's the reason why delta H of graphite is taken as 0 standardization.
Right.
Next, graphite and diamond both will have a dangling bonds. Dangling means at the terminal, see if the bond is forming, let's say here. Have you noticed the last carbons are still open for bonding or no? Because they have an unpaired electron on them. Correct?
Hmm.
So that means the last carbons in diamond or a graphite, they don't have any closed valency. They are open valencies.
Right.
So instead of only carbon and silicon attracting, anything can attract. Clear?
Right.
So since anything can attract on that end, it can never be pure, 100% pure. There will be always some amount of impurity within graphite and diamond due to dangling bonds.
Yeah. Okay.
Done? Right. Finished? Right. Next. Check. Intercalation compounds, which means these are heavy alkali metals like potassium, rubidium, cesium that can
Right.
invade the distance, invade the space between the layers. Okay. So
Okay.
here we can invade, here the metals can invade in between the layers, and their size is around close to 4 to 10 Armstrongs. So that's why as they invade the metals, if they invade the space here, correct, so they will have some distortions here. So metal can lose electrons easily and increases conductivity.
Right.
The last thing we need to understand is fullerenes, Buckminster fullerenes. Okay, see,
Okay.
these are produced by electrical arcs between graphite electrodes in inert atmosphere. And fullerenes are
Right.
small balls known as buckyballs. They could be
Keyballs.
carbon 60, carbon 32, 50, 70, 84, and so on. Most common one is carbon 60. Okay. And these fullerenes can be separated via chromatography. Okay. And C60 is the most common one, which will mimic the soccer ball. Got it. And carbon has sp2 hybridization, and each carbon has three carbon atoms connected to each other, just like in graphite. Okay, but they are not planar. They look like graphite, but they are not planar.
Bad, bad.
And pi bond is delocalized here, so that means there will be a delocalization of pi bond with the alternative double bond there. Next, it consists of total of 20 hexagonals and 12 pentagonals. Okay,
Okay.
and pentagonal rings are only fused with hexagonal ones. Okay,
Yeah.
which makes it the purest form of carbon because there are no dangling bonds, है ना? Because it is cyclic. So dangling bond की जरूरत नहीं है. It is not open ended.
I have no idea what a dangling bond is.
See बेटा, डायमंड है. डायमंड के एंड पे क्या होता है? The last carbon, is it bonded to anything else? It has only three bonds, no? Correct? So it has an open valency, right? So that means it can
I see what
attract,
you mean.
that single electron can attract something else, right?
Correct. Yeah.
So last atom ka, last carbon ka, we cannot say it is again connected to carbon only, right?
Got it.
It could be connected to something else which might be an impurity. Hmm?
So that's a dangling bond.
That's a dangling bond. So the dangling
Okay.
bonds are observed in graphite and diamond. बट क्या ये चीज पॉसिबल है बकमिंस्टर में? नहीं, because the last carbons are again bonded with the same carbon of that molecule because it is cyclic. Okay,
Hmm.
that makes it purest form because there is no open valencies here. Clear?
Right.
Any doubt?
Hmm.
So you can see how many hexagonal rings exhibit, and see all the hexagonal rings here exhibit the aromatic nature like this. Okay,
Right.
so this is the basic idea you need to have from group 14 onwards. Clear?
Hmm.